everyone, dear attendees. I'm pleased to present you Dr. Martin Becker for today's webinar session. Martin is a molecular biologist specializing in the detection and analysis of genetically modified organisms. With a PhD in natural science from the University of Hanover and over 10 years of experience in wet lab research, Martin has developed a robust expertise in molecular assays development for GMO identification, quantification, and traceability. During his postdoctoral tenure in Germany, he designed and optimized qPCR and digital PCR assays, established next-generation sequencing pipelines, and collaborated with academic, governmental, and industry partners to ensure regulatory compliance and scientific innovation in the field. Currently, as one of our application scientists, Martin continues to drive advancement in molecular diagnostics by supporting customers in implementing high multiplex digital PCR solution for complex genetics analysis, including GMO detection in agriculture and environmental samples. His deep understanding of plant biotechnology, regulatory standards, and advanced genomics tools makes him a trusted expert in the rapidly evolving landscape of GMO analysis. He will be demystifying GMO quantification with digital PCR with accurate, reproducible results to support precise event quantification across multiple crops. We will open the floor for questions at the end of the webinar. You can submit your questions under the question tab on the menu throughout the presentation. With that, please join me in welcoming Dr. Martin Becker.
Yeah, hello everyone, and thank you for joining today. So, thank you for the introduction, Mariam. I will directly go to the presentation which I prepared today for you. And as Mariam already mentioned, we will talk today about GMO quantification and screening using digital PCR as an accurate, reproducible result to support precise event quantification across multiple crops. So what we will do, we will start with a brief introduction, and then I will explain briefly what has been already mentioned in the official guidelines, so how we get from a seed to a sample, and what is the accurate sampling process. We will talk about accuracy and precision in digital PCR, and also generally PCR and NGS. We will talk about sources of uncertainty in PCR. I will explain the conversion factor and how we can use this conversion factor as a powerful tool. I will also show you step by step how we can analyze raw data from our digital PCR platform to calculate the weight per weight of your GM event. Then I have some examples from customers and for basically first generation GMOs, so GMOs which has a transgene, and a second generation GMO. The report just came out. This is a GMO which was produced by CRISPR. Okay, let's dive into the introduction. So basically, the European Union says that GMOs are not that cool and that they are not allowed inside of the European Union. And that's why the European Union tests for it a lot. So also other countries test for GMO events. And by that, there were some thresholds defined when we have a GMO or not. And for the so-called minimum required performance limit of each test, they defined that 0.1% of mass per mass for food is a threshold. Everything above this threshold is considered as GMO, and 0.9% for feed. So for animal feed, basically. Well, this is the name feed. So then we have M per M refers to mass per mass. This is the unit we want to measure in the end, and all of that is regulated in a certain EU law and followed by a certain case. And this case basically describes how we treat second generation GMOs in the European Union, basically everything which is done by CRISPR, tail and zinc fingers. To be able to measure a GMO, we need to have an accreditation due to a certain norm and for all qualitative and quantitative tests. We also have in the GMO area certain compound feeds. So this means these compound feeds can be, for example, multiple compounds like soya oil, as I wrote, or it can be a mixture of wheat and soybean. It can be also a mixture of maize and soybean. And we also need to know what is the mass inside of these compounds, which doesn't make it easier, let's say. And every GMO must pass a so-called interlaboratory test, which is a kind of audit for qualitative, quantitative tests. And the sample material was normally provided by the federal states until last year. Currently, it's a bit uncertain, but it was this case for the last years. To make it even a bit more delicate, each lab needs to provide data that the measurement of the GM event was free of inhibitory effects. A way to do that is, for example, that you measure an artificial DNA template together with your primer, which can consist, for example, out of a template, primary probes like a G-block, which you mix to your sample or the other way around and measure the performance of the quantification of that one. So if you're not able to measure these artificial DNA, then you know, okay, I might have PCR inhibitors inside of my sample. What are the sources of GMOs worldwide? So you see that in each of the slides, I have here a source where I got these data. Sometimes I modified it from there, but normally it's what it is. So everything what I say has a source is public available. And we see that most of them are soybean, maize, rapeseed, and rice, which are like the majority of over 80% of all imported GMOs in the European Union. These are all first generation GMOs, and they are all imported from USA, Brazil, Argentina, Canada, or India. What is now an accurate sampling process? So we need the amount of seeds and grains which needs to be processed refers to the grain size. We need to even process the sample, and we need to be sure that we mix the sample properly to have also even distribution of a GMO event, for example, inside of the sample. The sample must be milled to a maximum particle size of 0.5 millimeters. And by that, we need to process, in best case, a total of 3,000 grains or seeds. 3,000 grains or seeds. And how you process it, this might be another kind of problem, let's say, because sometimes 3,000 grains and seeds can be not much. If you look, for example, on wheat, which grains are pretty small compared to maize, for example, or soybeans. From after we milled that sample, we can take a subsample, which should be in best case 2 grams, but exceptionally it can be also go down to 0.5, but it should not getting less than that. We need to extract the total DNA out of these 2 grams to get a respective subsample. And from this subsample, this comes on the next slide, we need to then analyze a certain amount of DNA. So here we have a list of what are roughly the 1,000 kernels in grams. Even these values fluctuate from harvest to harvest because you can remember, if you think about that, you have that the samples are sometimes a bit older or sometimes a bit fresher. The amount of water inside of the seeds is also fluctuating up and down. And by that, we know, okay, that 37 kernels of barley might be not in every case 1,000 kernels. So it is also indicated that you measure that every now and then. But to get a rough number, we see, for example, that for maize, we have 285 grams to get 1,000. This takes us, if you think about that, we need to get 3,000 kernels, we go around roughly 900 grams of maize, which needs to be processed, which can be quite tough to get 900 grams milled to 0.5 millimeters particle size. Okay, now we have the subsampling and particle size during the sample grinding process. We see that when you have different expected amounts of your target, you might want to go for certain amounts or for certain amount of particle sizes, and as smaller you get, as better you get. So we only get a quite good measurement with very small particles. While the bigger the particles gets, it is, for example, more uncertain that you get smaller amounts of your DNA analyzed. When we look on the GMO percent, we see that only with 800 milligrams, we are able to target 0.1% of the GMO, which would be the threshold for the food. So once we have our subsamples, we typically extract DNA. This is normally done by CTAP, or we combine CTAP, for example, with the silica column, and also sometimes some magnetic bead extraction kits are common in the area. All of that is fine unless you have a good sample. I don't mind whatever kind of extraction you do, but we need a certain quality of the sample, which should be free of phenols and other inhibitory effects. We need good, clean DNA, which can be also, for example, used for an NGS. So that is a kind, let's say, a good parameter to test. Typically, you get around 200 microliters with a concentration of 20 to 15 nanograms. So we have not the problem that we have too less DNA. We have the problem that we have more or less too much DNA, and from that we need to analyze a proper proportion. So we get normally 5 microliters of these 200 microliters are analyzed, and we see here a table of what is basically how much copies we are expecting inside of 100 nanograms, and how much copies fits on one of the chambers of, for example, our Ruby chip. So our Ruby chip is the tool where the digital PCR takes place. So basically, we mix our DNA together with the master mix and the primer and probes inside of one of these chambers, as this gets then processed in our digital PCR machine, which is here the NIO. The current setup is the NIO Plus, and by that we can amplify and partition our samples at the same time. We see here that when we look on the theoretically realistic maximum amount per chamber, we directly see that 224 nanograms are the maximum which we can load, which are roughly these 5 microliters here. But 5 microliters doesn't fit on our Ruby chip because our Ruby chip only has 5 microliter analyzable volume. So by that, you need to see how much chambers you need to process to get a proper result. For maize, for example, it would be 2 chambers to be allowed to get the maximum out of the sensitivity you need. Here we see a list of what all comes into the sample preparation process, and all has kind of sources for uncertainty and sources which can go wrong. So there are some which are out of our hands, or out of my hands as a specialist for digital PCR, which are basically the pre-PCR workflows for sample homogeneity, sample stability, or DNA yield, integrity, particle size, DNA storage. So this is everything you need to do by yourself before you do the digital PCR or the qPCR. So this should be already kind of a standard operation procedure, SOP, inside of your lab. Which changes then as the PCR analyzes by itself. So primer and probe sometimes doesn't need to be changed, sometimes needs to be changed, depends. Also the PCR condition sometimes doesn't need to be changed, sometimes can remain the same. And PCR protocol is normally specific for the digital PCR. And then we have calibrant, which is normally not that important in digital PCR, because in digital PCR, we normally have directly a kind of endpoint PCR. We don't need a calibrant to say how much DNA or how much copies do I have inside of my measurement. Pipetting accuracy is not that important with digital PCR because we have always an absolute quantification, and if you have pipetting occurrences from, I don't know, one time you measure 5 microliter of DNA, and one time you measure 4.8 microliter of your DNA, basically you would measure the same total amount of copies in the end. You would just get different amounts of total copies in the end, but it wouldn't have the same effect as it would have in a qPCR. So the results are much more reliable here. For data evaluation, of course, everything is different. So we have a different machine and different software. I will show you next how we can use the software and the PCR instrument and how we get the data basically. So what is now accuracy and precision? So we have different standard PCRs, and also NGS is basically has the same trend here. So when we measure and do both of them, they are very good. Both tools are very good to measure accurate, but not precisely that something is there. So you know that, for example, if you go for an agarose shield, you repeat it 20 times, and then 20 times it's sometimes a bit more blurry. Sometimes you have a band which you have a pale band, sometimes you have a blurry band, sometimes you have an elevated band. You don't know why, but somehow you get a signal and you know, okay, there's something in it. I don't know how much, but it fluctuates a bit around the perfect result. And then we have also the possibilities that we are not accurate or precise. And you know that you measure a DNA 3 times, and one time is negative, sometimes it's one time is positive. Second time you have 2 bands, and the fourth time it looks okayish but ugly. So that is what we mean with not accurate and precise. For NGS, it's not that hard, but for NGS we have the same because sometimes when you have very low GM concentrations, it might happen that you are below the threshold of 5% of all reads, and then you are not able to measure, for example, a low concentrated GM. Okay, for qPCR, we can have all of that. So for qPCR, we can be not accurate and precise, we can be accurate and precise, we can be precise but not accurate, and we can also very accurate and very precise. Why is that? So it depends really much on the operator. When you have a standard operations procedure and SOP for all single steps, starting from the DNA extraction, ending in the data evaluation, you can be very much precise with everything. But this includes that you also need a pre-PCR, post-PCR room inside of your environment and inside of your lab, and that you need really every time somebody doing the same to get really good results. With that ones, well, when you have fluctuating personnels, it can happen that, for example, I just remember from my students when they started doing pure PCRs, that basically I ended up here and I had to repeat it. You know, there's a GMO inside, but you don't know exactly how much because one time it's a CT of 38, the next measurement is a CT of 35, and it's like it's in between of what it should be. And here, this only happens when we are measuring always the same proportion. I'll come back later to that. With digital PCR, basically we have the same master mix what we should have with a qPCR, but we partition these master mix to single partitions. And due to the maximum amount of DNA, what I presented before, we ensure that we have some empty droplets and that we have droplets which only contain 1 or sometimes even 2 DNA molecules. And by that, it's so much easier to quantify this rare mutated DNA inside of the bulk. Here, it can be getting lost because the wild type signals are so much present inside of your sample that it can be that you don't measure this wild type signal here. And with digital PCR, you are much more reliable on single measurements of single partitions. And also to catch the single rare mutation, which you actually want to see, basically, which you want to see out of the background noise, basically. So with digital PCR, we are normally pass directly the not accurate and not precise and accurate but not precise. We are always accurate and precise, but we also sometimes are precise but are not accurate. Why is that? So with Precise and not accurate means that you measure too less of your respective DNA, and by that you don't measure, you always measure the wrong portion of your DNA. And this can then yield to the fact that you are not able to measure, that you're always measuring, for example, 1%, but realistically it was 0.5%, and you're always a bit off of that. And this can have a reason because of things going on in the lab, that you load too less DNA, that you did improper subsampling, and all of that. So this technique is very sensitive, but also can be prone to a not accurate measurement if not set up correctly. Here I have an example, basically from our own postdoc. And we see here, this is a kind of measurement of a GMO. And this is basically what we see once it gets a bit lower concentrated. We have then the no template control, and the low abundant targets are dancing around the low template control. So this is basically what we are talking about when we are talking about that. So not accurate or precise, we get something like that. So we cannot rely on that. In the digital PCR, it's much better to see. So we have here a 1D plot. So these are on the x-axis is always like in the qPCR, the relative fluorescence unit, and on the on the y-axis and on the x-axis are just all partitions measured, which gets a kind of index. So this is why it goes to the left to the right. And we see reliable, we have only one drop, which is always measured, which is clearly positive. And you see also in the NTC, if you have one drop, which is clearly positive, and if you have in the NTC one drop, I would not trust these results. But if there's only one drop in the sample, which is positive, and the NTC is clean, then you might have one realistic drop. So how can we now get uncertainties inside of our measurement? So you see that basically everything adds a bit of uncertainty to our sample. The sample preparation, you might got it already with the mixing of the sample. The DNA extraction itself can be a source of uncertainty. And well, let's say the PCR analyzers, this is something which I have at least in my hand, because I know that with the PCR analyzers, we can be very precise. And with the PCR analyzers, also our digital PCR system gives you always the percent of uncertainty of each single analysis back. So I will show you that later. And the data evaluation. So this is much easier with the PCR because you don't need basically to calculate anything. So you need to calculate the percentage out of two values. You will see it's pretty easy to do. The conversion factor. The conversion factor is a very powerful factor necessary for each GMO measurement. So we see here this is a mice kernel, and we see this one has 3 different partitions. So I copied that from this poster from Mr. Gerdes, and we see that the embryo, for example, is normally contains one part of the female and one part of the male. The integument is only female, and the endosperm has 2 copies of the female and 1 copy of the male. So just imagine you have a hybrid, and a hybrid contains a GM event only in the male part. This would mean that you don't have it in the integument, and you have 1 copy in the embryo, and you have only 1 copy in the endosperm. But in total, you have here 2, 4, 5 copies. So you would get it would be not 1-to-1. So you have a factor which tells how much is your measurement wrong, and by that we need to correct what we measured, and for that the European Commission gives us a conversion factor. You also see that these ones have different proportions inside of our measurement, which doesn't make it easier for the single measurement. But that's why these conversion factors exist. And for each GMO event, we have one conversion factor, which we need to use later. So here we see one real example from our digital PCR. So this is raw data. We see this is a Ruby chamber. Inside of the Ruby chamber, we have this one, this black area here, which is a pillar. This is just a mask area, which is used for the droplet production process. And in this assay, we see here with this assay, we see here some droplets. The droplets are basically generated from this part and then towards this part. This is why we have here, for example, less droplets than more droplets on this area than here. And basically these droplets up here are the last ones which are generated. So, and in this assay, we see that we have in this chamber one positive droplet, this one. And if we zoom in, we see it directly here, looks also good. And we see also some of them which looks like they are positive, but if you zoom in, we see that this is just a lint. This is nothing. And the software automatically excludes that one. As a wild type or housekeeper, or however we want to name it, we see that, for example, for the housekeeper, we have 828 droplets, which are positive for the housekeeper. You see, these are evenly distributed across all droplets and looking fine. We also get the droplet size, which is measured in our IFUs for the Ruby chip, which is roughly about 0.22 nanoliters. Why is that important? Because I will tell you now how to calculate from these two raw data the exact concentration by hand. For that, we have this busy formula. Don't get scared by this formula. This formula is just it's pretty handy. We have N, or we have C, which is the concentration. Then we have D, which is the dilution factor. Here it is always 1 to make it easy. Then we have V, which is the volume of the partition. And then we have the logarithm 1 and minus P, which is the number of positive partitions. So you remember for one chip this was 1. And we have N, which is the total number of analyzed partitions. So if you go back here, it is one droplet out of 17,735. So if you just fill in these data, what we got from these two images, we get the number for the concentration in copies per microliter of 0.256 copies per microliter and 217 copies per microliter. So here we see the data which are provided by the software, and we see that somehow fits very well. There are some uncertainties for the last numbers because, let's say, the droplet size, I use 0.22 nanoliters, but it's indeed 0.22 and then a trillion number of single numbers in the end. But this is why, so we get to this result. It's in the same range. This is all what I need. And now we can directly directly calculate the amount of target concentration inside of our target. So we have here the same formula. So this is what we calculated before. And then we want to convert these copies per microliters to percent GM weight per weight. And for that, we need the concentration 1 and concentration 2. So 1 droplet versus 819 droplets. And we need to just multiply it with 100, divide it with each other, multiply it with 100, and multiply it with the conversion factor, which we get on the website of the European Commission. And by that, we end up, for example, so this is just a nonsense example, but then we end up with 0.115% weight per weight of the GM. That's it. So it's just this simple calculation needed to get from copies per microliter to weight per weight. That's it. You can even include that inside. So for example, the conversion factor can be directly included inside of the software as a dilution factor, which I mentioned before, which is here 1. If you directly change that to the conversion factor, you get directly the corrected results with the conversion factor. Together with the Poisson statistics, which says how much copies do I have per droplet, we can then in the end also give you an uncertainty of the measurement and say, okay, we have, for example, here 0.256 copies per microliter plus minus 20%, for example. Okay, now we come to realistic customer samples. So we got, for example, samples for Herculex 1. So here we have the Herculex 1 and the lectin, the reference gene. I guess it was lectin, but I'm not sure at the moment. Let me check. So we got here the single measurements of these results. Here we see the raw data and how they look like. We see we have some GM events inside, and we have multiple for the reference gene. The reference gene is measured in hex, and the transgene is measured in FAM. And here we get the single 1D graph. We see here these are all the negative droplets, these are the positive droplets, and here we have for the reference gene, we have the positive droplets, and here's the negative droplets. And on top we have also a 2D graph, so you can choose in the software how you want to see it. And the 2D graph, it looks like that. Basically, we have the single positive, which is actually Z graph, which is over here. Z graph is over here, and these are the double positives. In this case, these double positives are just the double positives by chance. This is a sample name in this area. We have here the copies measured per microliter for the transgene. Then we have the copies measured for the reference gene. So here we have also the name HMGA. Then we have the GM content in percent, the conversion factor, and the GM content in weight per weight. We have the fortification level, so basically what was expected to be inside of there. So, and then we have the consensus mean. So the consensus mean means this is the mean of all measurements inside for all labs who did the measurement for the inter-laboratory test of this single sample. So this sample has been measured around the world with tissue PCR and qPCR, and we get a consensus mean which is around 0.43, and we get 0.44. So perfect, but nobody gets 1. So this is somehow saying already that maybe the assay itself is not that good, what was provided, because everybody gets not that good data. Another example is the quantification in multiplex with for MIR 162 and MON 89034. So here we have 2 quantification events of 2 different GMs. We have visualized that in a 2D plot, and we see here the sample name again. We see unfortunately in German, the GM content for FAM and the reference for the hex, and the total amount for the GMO. And here we see how much we got as a total GMO content. So it's 1.84, and the consensus mean was here 1.25. So we say it was expected 0.8. So we see that here we are a bit off. So why I'm showing you data which are not that perfect? Because we are still in the same range. So we are still some of the data, some got even with other measurement with other measurement techniques the same percent GMO as we got. And why do we got this data? So I guess there are some reasons. So for example, I believe we loaded 2 less DNA. So we see here that we got 4,253 copies, and we can even go up much higher in the amount of copies measured. So we could add here much more DNA. From my perspective, also a restriction digestion can always help to reduce the genomic complexity and to increase the amount of to then increase the reliability of the single measurement. We don't have optimized this assay at all. This was the first try, and we cannot exclude that we have also subsampling error before in the entire process. So that basically the sample was mixed very well before we got the DNA and measured from the DNA a proper portion. I believe here that the main reason is that we just measured 2 less of the DNA. The next one, which we did together with the AcroLab group, was a 6-plex screening assay, which I personally think is quite promising. So we tested for all of these different transgenic regulatory elements. So the 35S promoter from cauliflower, the TNOS terminator from cauliflower, the figwort mosaic virus element, the chloroplast transit protein 2, and the cry insect resistance. we all had these ones in different fluorophores. These were not optimized for our system. We just got them, and I made it possible, let's say. So this is one really good thing about our system currently. So you can just use what you want, and somehow it will fit. And we got these data. So we got single positive measurements, for example, single positives of 35S, single positive for T-NOS. And sometimes you even got double positives, for example, here for CTP and for PMVS. And we see that there's a kind of coincidence. So all measured signals were all double positive for these two targets. This already tells us something. So we see that we know that these droplets contains CTP and PFMV. And if we then bounce back to what we measured, so you know in your lab what you measured, like rapeseed or maize, and then you directly know, okay, for example, we had soya, and this combination directly tells us it must be Roundup ready to yield. So MON 89788. If it would have been rapeseed, it would have been RT73. So this is a pretty powerful screening assay tool which can be used to prior screen what you need to look for. Here we just see what we then measured afterwards. So we have here the expected results, and I must say that we got some false positives. So here 0.35 is one positive droplet, 0.71 is two positive droplets, and 0.98 are three. So I must say when we measured that, we measured it very fast, very quick and dirty, let's say quick and dirty. So I'm not surprised that we have something which is here in the background. So it wasn't a pre-PCR lab, it wasn't a post-PCR lab. Everything was just fast, quick and dirty. So we had here the soya meal, which was expected positive in P35S, NOS-T, and CTP. And we see also that that is true. And additionally, we found PFMV. Why? I don't know. Rapeseed should have been only positive for P35S, but we found it also positive for all others, which well, let's say these ones did not has were not tested for this rapeseed sample at all in qPCR. So it was not expected, so nobody tested it. In this soya meal, we expected everything positive, and we see everything is positive. And also for the positive control, everything was positive. And for this rapeseed, we see that, for example, there was no P35S, but we had indeed PMV and CTP as well together. And CRY we had also, but well, they did not measure CRY in first instance. So we didn't know the concentration of CRY inside of that one before. Then we compared the simplex measurements compared to the multiplex measurements. And we see that for some samples, there are some differences. Also, we need to consider these are single measurements, and sometimes they work better, sometimes they work not as good. And here, for example, for that one, we see that sometimes it was really 0 compared to 6.64. But since they are single measurement, I would say I would not weight them too much. But sometimes they are also very much the same. So if sometimes it's just one droplet, which is positive, but normally they are basically in the same range. Even if you have higher concentrations, it's much more reliable. So we see not really something off here in the single concentrations or in this in something which would say where we would say, well, simplex measurement is superior against multiplex measurement. We don't see this trend here. Then we did a quantification assay for MON 8978788. So these are two different measurements for one color. So we had here lectin and MON 89788. And we run both as a singleplex reaction. Honestly, I don't think that this gives you a benefit. The only benefit is that you get these assay ready to use from the website of the European Commission. but I believe they increase the chance for pipetting errors. And the same assay would have worked as well in a three-plex assay with the lectin, the GM event, and inhibition control, which you could have just measured in the same at the same time. As a result of these GM event, so this quantification event, we see here the data. So we have the NTC where we indeed did not measure anything. Then we had 100% yield. So this was basically we expected 100%. I have here the concentrations for the lectin, the concentration of the GM, then the concentration in percent, and the conversion factor, the fortification level, so what was expected, and we see the measurement range from all previous measurements. And we see we expected, for example, for 100% yield, we expect 100%, we got 180%, which is from me in the pretty much same range. For a single measurement, it's fine. Then we got two measurements for QC yield, which should have been 1%, but we measured one times 0.4 on 0.08. So this is definitely off, and also off of the measurement range, which was from 0.43 to 1.32. So what is here the problem? We just measured 10 nanograms. To be able to measure 1%, you need to load much more DNA. By that, we just have the possibility to pool chambers together in our sample. And by that, for example, say together in our software and just say, okay, if we measure these two together, we measure in total 20 nanograms because we say to the software, okay, these two chambers, please treat them as one chamber. By that, we get, of course, an increased concentration of the reference gene and of the transgene. We get then what is most important, by the pooling, we get into the range of what we also expected. So we see pooling is a powerful tool when you have single measurements which don't maybe have too less of the DNA. This would be also a workaround if you have a sample which has inhibitors. You just can load less of this sample and pool them afterwards together. In that way, you will avoid to re-extract the DNA out of the sample, and you still get DNA out of that. Okay. As the last one, this was made with the Barrett system. So we had second generation GMO where we measured a single SNP mutation inside of barley. So this is a Cas9 mutation, which is homozygous in the PDIL gene. And this was measured basically in the background of 200 nanograms of barley genomic DNA. So why do I show that? Because let's say these kind of customized nucleases are the future in plant breeding, and I would say we are just waiting for the next GMOs, which are flooding the European market. And SNPs are just different kind of measurement compared to a transgene element. So SNPs are much harder to address, and in this work, which basically I initialized and then was followed by my then I started at Stiller and so somebody else finished it. But this we did together with a drop-off assay, which was basically in the bulletin 6407 on page 95 from Barrett Laboratories made, and we have here the results from the QX200. And we see that, for example, the barley wild type is visualized in green and the SNP is visualized in blue. We see that also for the green, we see some of the background noise. So these were LNAs which were used together for the forward and I'm not sure. I added them for the probe, but I'm not sure if they were also added later on the oligos, I must claim. But we see some background noise for the wild type. Inside of the channel for the GM event. Nevertheless, you can say what is positive and what not. So we see directly, you can see that. And if we check the linearity, we see that we have 0.9987, which is perfect. Even in lower concentrations, we just get perfect results here. So we see that also dPCR is able to analyze these SNPs since they are known. This is another thing. So another aim of the study was to find out if CRISPR has some kind of footprints in the background, and if we were able to find other off-target mutations, but which wasn't actually the case. So this is also one take-home message from the study, that CRISPR just does its job, at least in this barley plant. Okay, by that I already finished everything. So still, digital PCR itself is a very good solution for standard samples from interlaboratory tests. And I showed you that standard quantification assays can be transferred directly to digital PCR in first tries. But, well, let's say give a limited benefit to existing qPCR assays in single measurements. So to be very honest with ourselves, the lower dynamic range offer is a bit of a burden, but in the end, we have also fewer pipetting errors. So one needs to see what kind of setup fits best to them. But digital PCR is a key to high multiplex measurements, and quantification of several targets in one reaction is possible. And also we can quantify GM events, wild-type references together with inhibition control, which I see is a very strong tool for some labs. And the screening assays of first-generation GMOs are definitely a thing for future applications, and together with digital PCR for SNP detection for the second-generation GMOs. So by that, I thank you for your attention, and I guess the stage is now open for several questions, if there are questions.
Yes, thank you, Martin, for the presentation. It was full of insights and information. Please feel free to ask your own question in the question field on the top right of the screen. I will start with some that we already had. So first one was, why is it so essential to grind and mix the sample well before testing it for GMO?
Because you normally get 20 kilograms of feed, and inside of this huge amount of grains, you must find properly what is inside. It can be that, for example, there's just one grain on the bottom of the big portion, and you need to, by mixing it properly before you add it to the grinding, you ensure that it's not only distributed on the bottom of the box, and also on that it's distributed very well. And with the grinding process, you also make it accessible for the later on DNA extraction, because the smaller particles are then evenly distributed inside of the subsample for the DNA extraction.
Okay, perfect. Thank you. The second question was, how do you decide whether to use a single target test or a multiplex test?
It depends on what you want to see. So if you, the European Commission gives you normally single target test, and normally, if I'm not mistaken, they offered that you can also like start some multiplex quantification tests on their website. That's not that common still. From my perspective, it makes only sense if you want to measure the inhibition control at the same time, that you just reduce the pipetting errors. And I believe it's very powerful for screening assays, as I mentioned, because for the screening assays, you can directly see from the pattern of positive droplets, you directly see when it makes what kind of GMO you have inside of your sample.
Okay, perfect. Another question was, what makes digital PCR better than traditional qPCR in detecting GMOs, especially when there is only a tiny amount of GM content?
Yeah, this is a bit delicate because from my perspective, there is for the quantification not really a big benefit. If you have an existing pipeline, it works very well also with qPCR. So I'm very bad at selling. But let's say this is really a big problem, because for quantification you need to measure a certain amount, and a qPCR has just is more dummy proof for big amounts of DNA. But I see that for screening assays, the digital PCR would be much more powerful.
Okay, perfect. Thank you. And also we got another question, but it's regarding the recording. So for your information, you will be receiving the recording of this webinar 1 hour after, so it's mainly at 6 today. So yeah, just for people who are questioning about the recording. We'll go back to technical questions. So we have another one, which is the background observed is expected to be associated with the use of LNA.
Yeah, so you don't need to use LNAs. In the one assay we used it, this was for the CRISPR mutations. We used it because sometimes you get a clearer signal to distinguish the point mutation. But from my experience I have now, I would recommend to always just start without LNAs and just give it a try. Normally, there's a big chance that it works also without the LNAs. Maybe you can ask me, or maybe you can go deeper. What do you mean? So with the LNAs, do you need to know where you want to place the LNAs, or what is the benefit of LNAs, or so maybe go a bit more in detail that I can answer it a bit better.
Okay, so until we get a feedback, we go to another question, which is, so while using dPCR and low abundance targets, as you do with such a low amount of positive partition and the samples of interest, how do you consider the risk of contamination of your sample and or the analysis of limits of blank?
Yes. So the limit of blank is measurement. So just for myself and everybody else in the audience who doesn't know it, so limit of blank is you measure master mix and water and just check how big is the chance that you have a positive droplet just out of nothing. So this is the limit of blank. The limit of blank is normally, I would say, 1 in 16 chambers, so very, very low. This is, let's say, a good assay, it doesn't happen. But so if you consider now and look on a typical GMO lab and reference lab, you can be, so normally you are very happy when you have a PCR hood where you can pipe it. I would be very happy if you have that. Because then you can also just turn on the UV light and then burn everything which is not DNA, which should be inside of that assay. So I would really highly recommend that one as a minimum standard. And so you will be always able to see a reoccurring one positive droplet for a low abundant target inside of let's say inside of the technical replicates, and you will be always distinguish that just be able to distinguish that from the limit of blank or from the NTCs, because you see also the way this droplet appears when you have I showed that in the presentation. When you have a reliable one positive droplet, it will reappear always. And when you have a limit of blank and you have this limit of blank problem, it is very likely that you have one droplet which is somehow low positive, not really positive, and it's not a clear signal. So you will be able to distinguish between that.
Okay, thank you. We go to another question, which is, when you use an element-specific assay, is it necessary to use a correction factor based on the copy number of the element?
No, because so if I understood it right, an element is like a transgene element, so like TNOS P35S, and because these transgenes were produced with very ancient, very old-fashioned techniques like particle bombardment, we even don't know how much of the transgene is in the background. So hopefully there's one. Honestly, I don't know. And the problem is here, if you don't know, we can't really quantify the amount of these elements. And sometimes you have even two certified press promoters behind each other, or we don't know actually what is happening here. So this is why the screening assay for these elements can't be used for quantification.
Okay, thank you. Another question, which is, are there benefits in using drop-off assays for detection of a known SNP instead of competing duplex assays?
Can you repeat the last name again?
So are there benefits in using drop-off assays for detection of a known SNP instead of competing duplex assays?
Ah, so it depends. So with the drop-off assay, you directly have a reference inside of the same amplicon. This is this is basically a big benefit, right? So you can't measure that. You can't use the same assay in a qPCR because it won't work. Uh, so I see here is the biggest benefit that you directly know how much of the wild type is in there, and you directly know how much from how much mutant is there. This is very much, this is the biggest benefit for the normal duplex assays. So you can always run a competitive assay. So this is basically the same. It's just you have one probe for the wild type sequence and one probe on the same position for the SNP. And by that, you can then directly see which of one, how much wild type signals you have and how much SNP sequences you have. Also, that is possible. Yeah, so both of them work fine. You can also combine both. So you can also use a drop-off combined with a combined with a competitive assay. Also, that I would even say this is the most reliable assay because you don't have the false positive by chance.
Mm-hmm. Okay. Another question that states concerning validation of limits of detection, how should we handle the minimum amount of partition to consider a sample as positive, since current tools are optimized for qPCR where this is not an issue?
I agree. So it depends on the amount of DNA you load. So if you go, I had this list of how much DNA you should load as maximum, and you should also refer to that. So once you have a single measurement and you see that you are that you are very reliable able to measure that amount of, for example, for higher concentrations of a transgene, it's not a big problem. It's always getting just a problem when you have low concentrations of a GMO. So for a low concentration of a GMO, you will have the problem that in one measurement it's negative, in the next measurement you have one positive, in the next measurement you have two positives. So, but the same problem you would have in the qPCR. But in the tissue PCR, at least you have the possibility to pull all of them together, and then you know you have 60,000 partitions, and out of 60,000 partitions, you have 3 positive droplets. This is more powerful compared to what you can do with the qPCR from my perspective, because you get a very clear signal and you directly know this is positive, it works. Yeah, but in the qPCR, you can just load more DNA and compensate by that. But then you also make sure that the DNA does not inhibit the simple huge amount of DNA does not inhibit your PCR reaction. So it's complicated.
Okay. And we got a feedback from the person that asked regarding the LNA. So she sent another answer that state LNA usage, MGB, minor groove binder. Probes can also be used to increase specificity discrimination of similar targets.
Yes, but MGBs. I'm not against the company who provides them, but I would not use them. So they can work for a duplex competitive assay. So as I said, two probes competing between wild type sequence and SNP sequence. They can be used for that, but the chance is very high that the MGBs are interfering with each other, and then you will have a very bad signal. And this happened actually for my work at IPK back then, that we tried it with MGB and we had no resolution at all. It was just not binding at all. We had just no signal. This can happen, and this does not happen with LNAs. It's really up to you. So if you have an NGB that works great, use it. I'm happy with it. And there's also nothing I would say from the legal side which hampers you not using it. LNAs just, yeah, are from my perspective a bit easier to use once you know them. So briefly, if you want to use an LNA, put it at the spot or the position of the SNP. And if you want to be on the safe side, just there are two different ways. So the one way is if you just put on the position of the SNP and then the base next and right to it, another LNA, that you have basically 3 LNAs flanking the SNP. And the other way is that you put one LNA on the SNP and then you play with the other positions and see where it has the strongest effect on the matching temperature. So this is another possibility how you can use it. But you can use MGBs and you can use LNAs, not together, but there is no reason why to use one and the other one. But just in case of multiplexing, NGBs are not that good in multiplexing.
Okay, and our last question, I assume, it's please, what is the nominal partition number?
17K droplets, plus minus.
Okay. Yes, I assume that was our last question. Yes, we didn't receive anything else. And as I mentioned, we'll be receiving the recording of this webinar in about 1 hour from now. And you can still see, go through all the questions, all the answers. And if you still have any questions, please feel free to reach out either to me or to Martin via LinkedIn, and we'll be happy to assist you. Thank you so much and have a good day.
Bye-bye.
Bye.